So my name is Luke, as Nick mentioned. So I'll be presenting all the mechanical updates. And this time last year, or I suppose earlier in the year, last year, I presented all the material for R19.0. And since then, we've had 19.1, 19.2, 2019 R1, and as of about a week and a half ago, we've had 2019 R2. So I'm trying to compress all of that into about an hour. So basically, I'm condensing it down to all the good bits. So there's a lot more stuff that I don't have time to cover here. If you're interested in it, you can always just go to the help for 2019 R2 and go to the update bits, and it tells you everything new in great detail. So these are the new things I'll be talking about. I suppose the biggest one is this new interface in mechanical, new ribbon interface. So they've freshened everything up and given us a brand new, more Microsoft-like interface. So I'll show you a bit of that. Some stuff on the new keyframe animation, part transform tool within mechanical, which is pretty handy, external modeling, ANSYS composite prep post, some new features in there. I think this is my new favorite toy in R2, the semi-implicit method. So I'll show you that and give you a bit of a demonstration. Some stuff on distributed solving and cloud solving. New features in explicit dynamics. A general AXISYMMETRIC tool, which is really quite clever. Some stuff on smart crack growth and distributed solving in that. Material designer, which is my second favorite new toy in R2. And then some stuff on topology optimization, which will overlap a bit with what we'll be presenting next or later with additive manufacturing. Cool. Okay, so first things first, the new interface. So this is what mechanical looks like now. So it's more Microsoft-like. There's a ribbon across the top, or I suppose it's more Space Claim-like. So we still have the tree, that's all the same. Details window's the same, geometry window's the same, except what's here is different. We don't have a context bar anymore. Instead, we have a this context ribbon menu here. So whatever you click on here in the tree affects what you see across here. I'll give you a little bit of a demonstration on that. Also, all the icons have been refreshed, so it all looks like nice and new. One of the most useful and exciting features of the new interface is this quick launch search feature that's up here in the top right-hand corner. So if you're like me and you forget where the particular menu item is for a particular thing, you can just type a keyword in here. And in this case, we want to find out how to activate or deactivate the triad in the bottom left corner. So you just type triad, and then you can click here, take me there, and it opens up the window automatically. In the second example here, they want to find out how to change the location of the scratch space for solving. So you just type scratch, and it shows you in tools, options, mechanical, analysis settings, analysis data management, scratch solver, files directory. So it automatically brings you there. So it's really useful for people like me who get lost easily. You can also customize the key assignments, all the hotkeys. People have been asking for this for quite a long time. These are all the default key assignments for all the hotkeys, but you can customize them yourself. And you can also import and export them. So if you're moving to another machine and you want to take your hotkeys with you, you can do that. And we can store window layouts as well. So if you have a particular layout or orientation of windows that you like, you can save that to a layout, and you can have multiple different layouts for different workflows. And this is a great tool for speeding up, setting up multiple contact definitions. So if you're setting up, say, some manual contact definition, and you have to select the contact region and the target region. Previously, you had to go to the contact region, click on the yellow box, click on the feature here, go back and click apply, click on the target, go back and forth like this. Now you can do it all in the same location. And I'll show you in one of my demonstrations a little bit later how this speeds up your workflow. And then in engineering data, you're able to access the libraries from within mechanical. So you don't always have to go back to engineering data within the workbench environment. So you can just click on your material in the materials branch here, and then you can go to your structural steel. It shows you all the stuff in your library. You can get a summary of the material properties. You can search for other materials and access the library through mechanical. There's also a new materials library called the Granta Materials Library. Now, Granta are a separate company to ANSYS, but ANSYS and Granta now have an arrangement where they've embedded part of their materials library within mechanical. And you can also sign up to their full featured materials library online and get their materials library searching tool. And that interacts with ANSYS. So basically, as well as all these usual material libraries like the general materials, the composites, we now have this Granta materials data for simulation. So go into engineering data and have a look at what's in there. And there's some quite useful stuff. So it's quite a comprehensive library. Features all your usual steels, some elastomers, plastics, lots of different grades. And you can access all of that within mechanical. So there's linear isotropic materials, failure criteria, thermomechanical, lots of electrical properties, some temperature-dependent material properties, and hyperelastics, as I mentioned. So there's a lot in there. And unlike the default materials library, like the general materials and the general nonlinear materials, they're not just sort of generic materials. These are actually tested materials that Granta have in their library. So they're proper material properties. And this is how you search from within the mechanical interface. So you go into the engineering data within mechanical, and then you can type in this case, they want a multilinear brass material. So you just type that in, brings up all the brass materials with multilinear plasticity included in the material properties, and you can check them all out, check the curves, and then access all of that. So it's well worth having a look at that. Another great tool within the new interface is this commands object. So this has been refreshed and updated to make it more like an actual programming interface. So if you're familiar with using APDL commands within ANSYS Mechanical, previously it was basically just a text box and you type your text in or you copy and paste your text in. Now it's more like a programming interface in that if you start to type in a command like NS, it brings up all the possible MAPDL commands that could fit that criteria. And then when you select one of them, it brings up all of the arguments. So in this case, it's ncell for selecting nodes. And then we have all the arguments. And it highlights in bold the next argument that you want to access. So if you type in a bunch of commas to skip some of these arguments, it will always highlight the next one. So you don't have to count commas and then count which argument you're up to. So this makes command object usage a lot easier. And another thing that they've been, or the people have been asking for a long time, is the ability to combine workbench projects. So if you have an old workbench project and you want to bring it into your new one, you can just go to import and import an existing workbench project into your current one. It's a simple thing, but people have been asking for that for quite a while. Right, keyframe animation. So we've always had simple static animations, but now we can do it by keyframes. So this animation was generated within mechanical. And basically what you do is you take a couple of keyframes, so you orient your geometry in the location where you want, generate the keyframe, specify the duration for the animation, specify the number of subframes, and then hit play, and it generates an animation like this. So it's great for creating animations where you're exploring your geometry. And you can also synchronize it with your results. So I'll just hit play on this video. So if you click on this button here, it will synchronize the keyframe animation with the results animation. So in this case, we're playing through a von Mises stress plot, and we're also playing through a keyframe animation. So we can fly around our geometry as the simulation results evolve. And as I mentioned, these are the tools for controlling the total time for the keyframe animation, and then the subframe count, or the resolution, the time resolution of the animation. Okay, part transform. This is quite a useful tool. This allows you to modify your geometry within mechanical without having to go back to your geometry modeler. So if we've got some mechanical system here where this body hinges about this point here, if we want to have a look at a bunch of different load cases where this is in a few different orientations, we don't have to go back to Space Claim or Design Modeler or your CAD tool, modify the geometry, update, remesh, check your contacts. You basically just stick in this fella, part transform, into the transforms branch, select your geometry, select the coordinate system that you want to rotate or translate about, and then it applies the transform. And we can have multiple transforms, as you can see here, and you can change the order just by dragging and dropping. And you can also parameterize these. Sorry, one back again. So if you want to do a design study to have a look at, say, the stress that results from having this in a bunch of different orientations, you can parameterize the angle of rotation, for example, and run that through Design Explorer or OptiSlang. And we can also do a simulation template. So what this means is we can basically open mechanical without having geometry. So why would you want to do that? Well, if you want to build a template for multiple analyses. So we can open up mechanical, we can define lots of contacts, loads and boundary conditions, and then we define them using name selections. So these are all pre-set up name selections. They don't have geometry fixed to them yet. But basically, once you've done this, you've got your analysis. The only thing you don't have is geometry. So then we can just import geometry with either predefined name selections, or you can define the name selections when you bring them in. And then when you bring it in, your simulation's automatically set up, and you just have to hit solve. And then if you want to run a different geometry, you can just go up here, replace geometry from file, import a whole new geometry with the same name selections assigned to it, and that will automatically set up the next simulation. So all you have to do is make sure your name selections are set up, and all your loads and boundary conditions and contacts are referencing the correct name selections, and then you can just replace the geometry at will. And you basically have a template simulation. A few other things. There's a quick save within mechanical, so you don't have to go back to Workbench to save. You just go to File, Save Database. There's a little icon here that tells you if your analysis has been saved recently. If there's an asterisk next to it, it means it hasn't saved the most recent changes. And we can parameterize the solve time. So this analysis took 4 seconds, and as you can see here, we can parameterize that and run design studies looking at the effective stuff on the solve time. Okay, bolt pretension. People have been asking for this for quite a while. In fact, pretty much every time I do a training course and I talk about bolt pretension, somebody asks, if I have 100 bolts, can I apply one bolt pretension feature to all 100 bolts, or do I have to define 100 separate bolt pretension features like this? Well, now you can. So we've got one bolt pretension, and it's assigned to all of these. Well, in this case, it's just 4 bolts. But it's much quicker than having to set up multiple bolts with lots of different load and lock steps. So it's a big time saver. There's a few new joints. Let's get that running. That's the distance joint. It's fairly self-explanatory. Maintains a constant distance between this location and this location. A screw joint. And a CV joint, which will appear now. Here we go. So these are all available in the mechanical GUI now. Cool. ACP. So for those of you who aren't familiar, ANSYS Composite Prep Post is a pre-processing and post-processing tool for complex composite analyses. So there's a few new features here. The draping tool is a tool that we use for predicting the shear angles of the fabric when we drape it over complex geometry. So here we've got a bit of a helicopter. We want to model it with composite materials, so we drape a fabric over it. And when we drape the fabric, it shears, obviously. And if we want to do an accurate finite element simulation, we need to know what the new orientation is of the fibers and what the angle of the shear is. So that's what the draping tool does. Previously, we could only use it accurately for woven materials. So there's a woven material. And this is a contour plot of the shear angle that you can see through there. Now it supports unidirectional fabrics. So this is a unidirectional fabric, and as you can see, it has a very different shear angle around here. There's also there's a parameter for controlling the spreading of the fabric. So being a unidirectional material, there are no transverse fibers to constrain it from sort of spreading in the transverse direction. So this transverse parameter allows you to predict that as well. There's a new cutoff feature for solid geometry import. So we had this previously for solid element meshes that were generated within ACP. So if you have a particular concept composite layup, you could generate a solid element representation of that within ACP. And then if you had some manufacturing process that was post-layup, where you might grind a bit of the material off, you could import a surface geometry that would essentially cut the solid elements and give you this. So this is your post-layup, post-machining part, and then you can go and simulate that. But now this also supports the ability to import a solid mesh that you generated outside of ACP, as well as solid element meshes that were generated within ACP. And then finally, we can do contour plots of material properties. So this is a contour plot of the Young's modulus in the one direction for an orthotropic material. So once we've done the draping calculation, we can then check to see what the local material properties are. So we've draped some fabric over this wing part. I think it's a wing. And then did a contour plot of the E1 Young's modulus. Right. So as I mentioned, this is my new favorite thing, semi-implicit method. I think this is really clever. So basically, it is a new tweak to the ANSYS implicit solver that allows it to switch from the implicit finite element method to the explicit method if we're having convergence problems. So this is fantastic for post-buckling sort of problems, crushing analyses, those sorts of things. So any post-buckling analysis is very difficult to do with the implicit solver. We usually need some sort of numerical stabilization tricks or the arc length method or something like that. So now we have this tool. It's only supported with MAPDL commands, so it's not a GUI feature yet, but it's really easy to use. And I'll give you a quick demonstration. So it has one command, semi-implicit. In fact, if you just type semi-implicit into a command object, it'll work. But there are a few other options like specifying the time step size that you want to use, changing the amount of output that it writes, and a few other bits and pieces. But basically, it's good for these sorts of analyses. So here's the crushing of a bottle. So you can't solve that problem in implicit alone. It has convergence difficulties, so it automatically transitions to explicit and then solves the problem. This is a ball hitting a net, so this one switches back and forth between implicit and explicit as it hits problems in the solve. And then the good old crushing of a tube. So these are all extremely difficult to simulate with purely implicit solver. So I'll give you a very quick demonstration. I'm not going to solve anything, I'm just going to show you a model that I set up previously. So here's some sort of bottle made of plastic. And if I show all bodies, I'm squashing it between two platens. Oops. Just drag that cable over there. Now I have a couple of contact definitions. So contact with the top platen, contact with the bottom platen. And because this is a crushing analysis, this is going to undergo self-contact. So as it bends and buckles and folds over itself, it's going to contact itself. So I've defined this contact between identical surfaces in the contact and target. That's that. Mesh, all good. And let's just hide this so we can see it a bit better. In the command object, I've got semi-implicit. That basically activates it. I've specified the time step size I want to use, so it'll activate a bit of mass scaling, and by default it wasn't writing as many result steps as I wanted, so I told it to write a few more. That's basically it. And if we look at solution information, sorry, first I'll show you the force convergence. Okay, so this is your typical force convergence plot. It's going along nicely, lots of green lines, which we like seeing, and then suddenly it fails to converge. So at this point here, it's switched to the explicit solver. Now, because it's not a GUI feature yet, we don't see anything happen there. But if we go to the solver output and scroll down, that's going to take too long. Here we go. So there's our usual implicit convergence. And you can see here it says transitioning to explicit method. And now it's time stepping using an explicit method instead of an implicit method. And then that marches on and solves. So if you want to have a look at that, let's generate an animation, 20 frames. So this would normally fail, well, an implicit would fail right now, but the explicit solver allows it to continue on long past the point of buckling. And then we have the self-contact as these parts contact with the other parts as they fold over. So if you're doing anything involving post-buckling, or just anything where you have large deformation and convergence is a problem for you, try out the semi-implicit method. If you don't know how to, give us a buzz on support. Yeah, I think it's a really great new feature. Okay, distributed solving. So now everything is supported in distributed. Previously, there were some unsupported features that weren't supported in distributed, and we had to use the shared memory parallel method. Now everything across the board is supported, and it's the default. So when you hit solve without changing anything, it's going to use distributed. So that's good for solve times, because distributed is always a bit faster. So it supports smart fracture. I presented this in the R19 update seminar, where we have a crack propagation using a lot of remeshing, some clever remeshing there. So that supports distributed now, and as you can see, we're getting good scaling, up to 32 cores here using distributed. So that's in R1. Now the load balance ratio is this number here that you can see in the solver output. This load balance ratio tells us how well we're distributing the solve. So in this case, a value greater than 4 is giving us bad load balancing. Basically what this means is if we're using, say, 8 cores, we want all 8 cores to be doing 1/8 of the work. Sometimes if you have a poorly distributed solution, you might have 2 or 3 cores that are doing lots of contact calculations, and then the rest of the cores are basically waiting idly, waiting for the other 2 cores to catch up. So this isn't a well-posed solution. So this load balance ratio gives you a bit of an indication about your analysis, whether it's distributing well. And contact is a typical, is often guilty of giving you a bad load balance ratio. So there's some new tools for fixing this. It's this CNCH command. And it basically allows you to split up large contact definitions and distribute it across the cores better. So we have an automatically split option, a manual splitting option, and a merging option. And basically the idea is we can take a large contact region and we can split it up amongst multiple cores, and then each contact and target pair will be solved on the same core. So there's no cross communications between pairs. And it looks a bit like this. So there's an engine block. We have a gasket in there. This is the original contact surface and the original target surface. So these surfaces are talking to each other. And we're solving on 9 cores, so we want to split it up into 9 contact pairs. So you can see this is one contact pair, the green one here, and then that's the target. And then magenta, so there's another pair. So basically we're splitting the contact up into 9 separate chunks, and you want to get the contact and target pairs matched correctly so that this region doesn't have to talk to this region on a different core. So this really improves your load balancing by doing this. So this graph just shows you a bit of a performance improvement. So the green line down here is just R19. 2019 R1 is this line. So this isn't using that splitting option. This is just showing you general solver improvements. And then if we activate this splitting option, you can see there's a massive improvement in the solver rating. Okay, cloud. Right, so rather than try to explain this to you, I'm going to play a video that explains the cloud solving to you. But basically, it allows you to access cloud solving on ANSYS servers from within the mechanical interface. So let's have a look at that.
In this video, you'll see a quick demonstration of using ANSYS Cloud to access cloud-based computing capacity. Start in your familiar desktop application with a model that's ready for solution. Then, log into your cloud account, create a new job, choose the closest available data center, pick from a set of predefined hardware configurations that are optimized for the solver you're using, and submit your job to the cloud. Input files are encrypted, transferred to the cloud, and HPC resources are provisioned on demand. Once the job starts running, you can monitor progress directly from your desktop application, where you have access to the full solver transcript and even graphical convergence monitors and trackers. You can also leave the desktop application and monitor your job from the cloud portal, using your web browser, where you have access to all of the same monitoring tools, and yes, this works for mobile devices as well. You'll get an email notification when your job completes. You can then go back to the web portal and take a look at your results. Right there in your web browser, you can create contour plots, vector plots, and section cuts in order to visualize and interact with your 3D results while the data is still in the cloud. And yes, even this works on mobile devices. To use the full power of your desktop applications, download the results to your local workstation to perform detailed post-processing as you do today. So far, everything I've shown you has been in ANSYS Mechanical, but all this works for Fluent as well. Submit jobs directly from the standalone Fluent application, choose from hardware configurations that have been optimized for the Fluent solver, monitor runs from the desktop app or from the portal, visualize 3D results in the cloud, and then download to your desktop for detailed post-processing. This is how easy HPC should be.
Right, so where we think that'd be particularly useful is for users who are usually perfectly happy with the standard 4 cores that you get with your normal license, but then you have occasional need for more cores. So rather than having to always have lots of HPC licenses that you don't use all the time, you can just submit to the ANSYS cloud and solve on the cloud there. So if you're interested in this, you can come talk to our sales guys afterwards. Okay, other solver stuff. This is some tricks for reducing the file size, the results file size. With the outres command, there's a few new options for activating or deactivating the writing of some output types. And then there's a new compression algorithm for the results file. So these are the new options for the outres command. So you can activate or deactivate element temperatures, contact data, nonlinear data, heat generation, electromagnetics, elements, source current densities, back stresses, and surface stresses. So all of these you couldn't activate or deactivate individually. They basically came as a lump. Now, the new compression option will automatically compress your RST file as you're solving. So these are examples from the ANSYS technology guide. So each one of these analyses is a different type of simulation. So they're different model sizes, so different numbers of degrees of freedom, different types of physics, different types of loads and boundary conditions and time stepping, those sorts of things. So as it's solving, it basically compresses the RST file. And you can see we're getting about 25% file size reduction, which is quite good when results file sizes can be in the multiple gigabytes. Okay, explicit dynamics. So the explicit dynamics tool, if you're not familiar with it, is the mechanical interface using the Autodyne solver under the hood. So the new feature in R2 is step awareness. So previously, when we set up an explicit dynamics analysis, you set up a beginning time and then an end time, and then everything was just solved between those 2 times. But now we can have multiple time steps, just like in a mechanical implicit solution. So we can have loads and boundary conditions activated or deactivated at a particular load step. So this is much easier than previously, where we had to know the time and then specify a load curve over time where to change the behavior of the load or boundary condition. So now it can all just be done with time stepping. And it also supports tabular acceleration. I've wanted this for a long time, but basically instead of having a constant value for the acceleration boundary condition, we can now specify a load curve. So the acceleration varies over time. It doesn't support an equation yet or a function, but you can easily calculate that in Excel, for example, and then copy and paste into the table. And in the probes, the solution output probes, they now support hourglass energy and contact energy. So previously, if you wanted the energy, you'd have to insert one of these probes. And these probes don't have very high resolution data because this data is extracted from the animation results file, which we don't write very frequently because they're very big. Whereas these trackers, sorry, I called them probes earlier, these are trackers. These trackers, we can get the data at every single time step. So this is very high resolution data. So if we want the hourglass energy or the contact energy for impacting surfaces, we can now get that via trackers. And there's a new feature for controlling how the contact operates as well. So with an explicit dynamics model, because there's a lot of rigid body motion and stuff crashing into other stuff, we don't always know what surfaces are going to impact other surfaces. So we just use the body interactions tool, not a manual contact definition where we select individual faces. It's a much more robust. The downside of that is, if you have multiple body interactions set up with, say, different friction coefficients, you don't always know which friction coefficient is going to operate between which body. So now we've got this pairwise option, which gives us more control over specific friction coefficients between which body. So we can use this body interaction tool to ease the setup of contacts, but we can have a lot more control over specifying individual contact friction coefficients. Right, Elastiner. So this is Elastiner within the mechanical interface. A few new features here as well. So this is the reinforcement feature. We've had this in the AutoDyn explicit dynamics tool for a while. Basically, it allows you to model beam reinforcement within solid elements without having to have coincident nodes. So the old approach of modeling, say, reinforced concrete, is you'd model your reinforcement with beam elements, and the nodes of those beam elements would have to be coincident with the nodes of the solid elements, and you would either use constraints or have matching nodes between the beams and the solid elements to transfer the load. So this body interactions reinforcement feature allows you to have completely independent meshes between the beam elements and the solid elements, and the beam element nodes are constrained to within a particular parametric location inside the solid element. So you can do these concrete reinforcement models or steel-belted radial tires where you have beams representing the steel radials inside the rubber solid elements. And we can also do a steady-state thermal analysis prior to an Elastiner analysis, and then feed the temperature results into the Elastiner analysis. So we've always been able to do a fully coupled thermal structural simulation within Elastiner, but this allows us to do a prior thermal simulation as a setup for the Elastiner. And then we can also feed the deformed model from the Elastiner analysis into a structural analysis. So here we've switched the order, and we've got an Elastiner simulation, in this case a metal forming simulation, because that's what Elastiner is great at. And then that feeds the deformed model into the static structural, and we can take the manufactured part and apply static loads to it. Okay, rigid body dynamics. There's a new type of integration method. It's the stabilized generalized alpha time integration method. The old version is just the generalized alpha time integration method. So for constraints and joints, the generalized alpha time integration method used to introduce some corrections at every time step. And those corrections used to introduce some spurious vibrations or oscillations in the analysis. And it also required some more iterations in the solution, which made the solution take a lot longer. So this stabilized generalized alpha time integration method removes the need for that. So we reduce the spurious oscillations, and also the solve time is much lower. So this is with the older solver here and the newer solver, older solver, newer solver. So yeah, it speeds up the solution quite considerably. There's on-demand CMS expansion. So if we're doing a component mode synthesis analysis where we're doing a rigid body analysis, but we had a few flexible bodies, you'd use the component mode synthesis method for that. And then when we wanted to post-process, for example, the stress in the flexible bodies, we would have to do the expansion step, where it expands all the stress results for the flexible analysis. And this takes a long time. There's a lot of I/O, disk I/O, and the results files are huge. In this case, it's 3.5 gigabytes. This new method, rather than expanding the whole thing, just expands what you need for that contour plot. So the on-demand expansion only takes 22 seconds as opposed to 4 minutes, and there's no results file, so it doesn't require this 3.5 gigabyte results file. So it's much more convenient than the old method. Yeah. Cool. A few other things. That worksheet for step awareness in explicit dynamics, that carries through to rigid body dynamics as well, so we can do the step awareness just like in explicit dynamics. We can define the restitution factor as a parameter. We can output more contact force definitions or information. And there's also an option for printing body forces for a particular body. So you can take a snapshot of a rigid body and output the body force balance. Right, general axisymmetric. So this came out as an MAPDL feature a while back, but now it's available in the GUI. And what this does is it allows us to have a 2D axisymmetric body within a 3D simulation. And we can apply 3D loads to it, so they don't have to be axisymmetric loads. So this is what it looks like. As we normally do for a 3D analysis, we tell the analysis type to be 3D. Then we have well, you can't see it here, but there's a surface body in the geometry. We specify our general axisymmetric boundary condition. And we specify the number of nodal planes. You can see the number of nodal planes there. And we basically solve it, and that's what the mesh looks like. So it's still a 2D analysis, but exists in a 3D world. So I'll show you what this looks like. Rather than talk to slides, I think it's easier to understand in a demonstration. So here's my 3D model. I have a 3D solid body here, and then I have a 2D axisymmetric body there. So I go into symmetry, I will insert a general axisymmetric feature, scope it to that body. Now I need to tell it, I need to give it an axis of symmetry. Now conveniently this lines up with the x-axis in my global coordinate system, so I don't have to worry about that. I'll give it 12 nodal planes. So you can see there the nodal planes now. I will define a contact. So I'm going to insert a manual contact region. So the contact side, so this is a new feature in the new GUI. I can just select the edge, select that edge here, and instead of having to go back and hit apply, I can just click here and say, that's my contact. And then I can select this face and say, that's my target. So I don't have to go back and forth. It's much quicker and easier for setting up multiple contact definitions. So this is going to bond the outer surface of this axisymmetric body to the inside surface of this ring. And then I'll generate the mesh. Right, so there's our 2D axisymmetric body in our 3D world. And I'll put some boundary conditions in here. So I'll insert a fixed support. And I'll put a force. So I will, remote force. So select that edge, insert a remote force. Set it to rigid. And I'll set it to 10,000 newtons in the Z direction. So you can see I've selected an edge, but because it's a general axisymmetric body, it's applying it to the full surface of the 3D body that it represents. So then I hit solve. So that obviously is not an axisymmetric load, so you couldn't do that in a normal 2D axisymmetric simulation. It wouldn't make sense. And we're solved, and there's the total deformation. So I'll just animate that. So that's solved in, where is it? 5 seconds. Now, if I have a look at my 3D equivalent model, it takes a lot longer to solve. So I'll just let that open. So there's 3D geometry instead of 2D axisymmetric geometry. My mesh, more or less the same deflection, 0.08 millimeters, and that took 1 minute 4 seconds to solve. So it's a lot faster. So anything where you have axisymmetric geometry, but you have non-axisymmetric loads or boundary conditions, try this general axisymmetric method. It's quite clever. Right. Smart crack growth. So this supports a few new features now. I showed this in the 19 seminar. It's basically using remeshing to simulate crack propagation. So it supports temperature loading, surface pressure loading, and multiple cracks as well. So you can see we have multiple cracks, and as we load up our body, you can see the cracks propagating and all the remeshing occurring at the crack tips. And eventually these cracks coalesce and meet each other. So yeah, we can simulate multiple cracks with the smart method now. And this is the thermal load. So we can apply a temperature load or a thermal load to a body, and due to the shrinkage effects, that's going to cause the crack to propagate. And also, as the crack opens, we could have pressure being applied to the newly opened surface. You can't really see it here because the crack's quite subtle, but as the crack opens, the pressure is applied to the inside, so the newly created surface of the crack face, and that causes the crack to propagate further. Right, Material Designer. I'll demonstrate this as well, but basically this is a tool that allows you to calculate the orthotropic material parameters for composite materials or lattice structures like these. So in R2, it supports a whole bunch of new lattice structures. So if we're doing a 3D printing simulation with using lots of lattice structures, we can calculate the orthotropic material properties for these, and we don't have to mesh that geometry. We can just use a smeared approach. I'll do a bit of a demonstration of that. The other new feature is it supports randomly oriented composite materials like chopped fiber composites, but with some sort of bias in the orientation of the fibers. So if we have a chopped fiber composite, but most of the fibers are aligned to the x-axis, then we can put in like a bias factor that will calculate that. So I will demonstrate that. Material Designer. So it's down here. To see how I'm going for time, not too bad. Material Designer. Okay, so what I need to do is I go into Engineering Data, and I'll go into Composite Materials, which is there. Now I need carbon fiber. So this is the material properties for just an individual fiber. It's not for a woven composite or composite and epoxy or anything. It's just individual fiber. And then I also need the resin epoxy. So I'll click on that. So I've got fiber and epoxy. Now I go into Material Designer. So this is in the space claim interface, which is nice. So it's really easy to use. So it's basically a tool that automatically generates the geometry for, I think I have a license warning. There we go. Yeah, it automatically generates geometry that represents a unit cell for our composite material, and then it meshes that, runs an FE simulation, and then extracts the orthotropic material properties for that, and then feeds that into engineering data, and then we can do a simulation with a proper composite layup. So this is it here. We can do lattices, unidirectional composites, random unidirectional composites, chopped fiber composites, a woven composite, which is what I'll do, particle reinforcement, or a user-defined option. So I'm going to do a woven composite. So I'll choose for my matrix resin, and for my yarn carbon fiber. Go to the geometry, so I can specify the fiber volume fraction, whether it's a plain or a twill weave, the shear angle. So when the fabric shears, it'll have different mechanical properties. I'm just going to leave it at 0, and I'll show you other shear angles in a moment. Yarn spacing, the fabric thickness, I'll just leave the defaults at that, and I'll hit the tick. So this automatically generates the geometry for that unit cell. So there is a couple of fiber bundles in a unit cell. And then I'll generate a mesh. I'll just give it a rough sizing. The tet meshing is perfectly good, but we can use the block meshing approach as well. So there's our mesh. So you can see it's all stitched together, no contacts or anything in here. Analysis. So we do orthotropic, so I'll just say yes. And now I have constant material properties. So I click that button and hit the tick. So that's basically going to solve this FE model. So you can see it's all sort of pre-canned and automatically set up, so I don't have to create geometry or anything. I can just specify the rough material constants. So it's very useful for someone who's doing composite layups where our materials post-layup don't really match the sort of standard material property data. So when you get material properties for, say, carbon fiber in resin, it's for a particular fiber volume fraction. And your manufacturing process may give you a slightly different fiber volume fraction, which will give you very different mechanical properties. So to get a good FE model, you need to have the correct mechanical properties. So we can use this to calculate that for us. So that's all done, and we look at our results, and we have our Young's moduli in the 1, 2, and 3 direction, shear moduli, and the Poisson's ratios. And then I can just go into engineering data, which is here, drag that in there, update all of this, and then yes. And there's our new material property that we've just calculated, and you can use that in ACP or whatever you like. Now the really clever thing is, I won't simulate the whole thing, but I'll just show you very quickly. So I'll just close this one. So if I'm doing a draping simulation, I'm going to have a variation of shear angles over my model. Some parts where I have complex curvature in the geometry, I'll have high shear angles. Other flat parts, I'll have a zero shear angle. So I need to be able to tell ACP what the mechanical properties for that are. So in this case, I've done a variable material evaluation between 0 and 20 degrees at 5 steps. I've solved it, and then we look at the results, and you can see we've got the material properties for all those different angles. And then if we go into engineering data, you can see they have a curve here. So this curve for the Young's modulus versus shear angle gets fed into ACP, and we can use that for our analysis. So it's a really clever tool for cases where we don't have test data, basically, for our composite materials. So that's the material designer. Right, topology optimization. A few new features here. We'll be talking more about topology optimization. Alan will be talking about it within the Creo context, and I'll be talking about it within the ANSYS and additive manufacturing context next door a little bit later. So the new features in the ANSYS topology optimization, it supports thermal compliance. So if we're doing a thermal-based topology optimization, we can do that. And we can do a topology optimization based on both temperature and structural analyses. So I'll show you that in a moment. Supports stress constraints in regions outside of the optimization region. And we can optimize shell bodies. And also there's a smoothing option for when we export the STL. So this is the thermal analysis. So we have a steady state thermal analysis here that feeds into the topology optimization. And we want to minimize the thermal compliance, not the structural compliance in this case. And here's an example of some plate body. So we might have a temperature boundary condition up here, and the temperature propagates through this body, and we're minimizing the thermal compliance. And this is the topology optimized part. And this is a case where we're optimizing for both a structural and a thermal analysis. So there's our thermal analysis, there's our structural analysis, and we want to minimize both structural compliance and thermal compliance. So this is the part that it comes up with using topology optimization. Now this is the stress constraint outside of the optimized region. So previously, if we did a topology optimization and we want to minimize or have a target von Mises stress, for example, in a particular location, it had to be within the region that we're optimizing. But in this case, we're only optimizing the blue bit here, and we're leaving this part alone. But we don't want the stress in this other part to be above a particular value. So we can set that as the target stress. And so this is outside of the optimization region. And then this is the optimized part that results from that. So basically, we don't want to load up this part, but this is the part that we're actually modifying. And we can do shell bodies too. So this is a shell or surface body. It doesn't optimize through the thickness, it's just the surface. And when we export the optimized part, there's a smoothing step, an optional smoothing step. So we right-click on topology, deformation, and we can either export it directly and get this, or we can tell it to do a smoothing step, and it gives it a much smoother STL. And we can take that into SpaceClaim and do more steps to smooth it or improve it, and then do further analysis or do 3D printing with that. And then finally, this is the last thing I'll talk about. It's still beta, but it's worth talking about because it's a really nice feature in topology optimization. It's basically a new solver called the level set topology optimization solver. And to access it, you go to Tools, Options, switch on beta features, and then switch on this level set method, topology optimization. And then when we do the topology optimization, we choose the solver type here, or the optimization option, level set. And just to show you some examples, so these are using the level set based approach. So the quality of the optimized part is much, much better using level set as opposed to the older method. And here's another one. So you can see this would require minimal intervention after topology optimization to smoothen this up. You could take it into space claim and you really wouldn't have to do much at all before you run another analysis on this or do some 3D printing on it. So worth playing around with. It doesn't support all of the manufacturing constraints yet. So hopefully next release it'll support all of the features. But yeah, it's still quite impressive.